I want you to go ahead and start on this and work on this until the bell rings, okay? You've got about 6 or 7 minutes until the bell rings. And this is where we're going to pick up next time, okay? We're going to hit the ground running. You'll put out that one. Do you have to do both? Even though, I'll change Canvas today, but even though Canvas says you have to do both of these, do you have to do both of these homework check understandings if we haven't finished the lesson? No. I'm still figuring out the timing on this, how long these lessons take. So sometimes we'll flex a little bit, okay? So you are responsible for the first, check your understanding, and then I want you to work on this until the bell rings. How fast does a penny fall? All right. And then 226, right? So we were just simply evaluating, correct? This is evaluating. So whenever I see a table of values like this to tell what type of function it is, the first thing I'm going to do is look at this. Every time the time is going up by what? 2. So anytime you see something like this, it's a very good idea to compare the time intervals. Are the time intervals all the same? It'll keep you from making a mistake. They are here, aren't they? So if this were linear, we should see the same progression in the bottom too, shouldn't we? But as we do this, we notice it's going down by 64, down by 192, down by 320, and then down by 448, right? So it is not linear, is it? So now it says find the exact time when the penny reaches the ground. That would be when height is what?
0.
Yep, so we said h of t equal to 0. In other words, we are looking for an x-intercept, aren't we? All right. Don't forget, that's what that means. So we set 1250 minus 16t squared equal to 0. And we get t equals approximately what? 8.83. Now, normally if you took the square root of both sides, it'd be positive and negative. Why did we throw the negative away? Can we have negative time? No, you can't have negative time. We can't go back in time. Time's only ever positive, isn't it? So we have positive time, so we throw the negative away anyway. So 8.83 seconds. Now it says find the average rate of change, the penny's height during the total length of its drop. So the total length of its drop, in other words, it's change in y over change in x. Change in y is going to be 1,250 feet, or negative 1,250 feet, because it's starting at 1250 and going to 0, right? All right, divided by 8.83 seconds. That gives us negative 141.42 feet per second. Now, some of you did this as positive. Be very careful, all right? Be very careful that you're doing it rate of change. It starts at 0 and goes to 1,250 feet, meaning that it's negative, okay? Determine how many feet the penny fell during each 2-second interval. I did that, didn't I? It fell 64 feet, 192 feet, 320 feet, and then 448 feet. What did we notice? It's getting what? Yeah. The distance is increasing, right? Each 2-second interval increases, which means we know that it's what? Probably speeding up, isn't it? Okay, if they asked you what did that mean, that means that it's speeding up. But they ask us that in 6, don't they? So now it says time interval average rate of change. So we said this was what? Negative 32, negative 96, negative 160, and negative 224. Did you find that? Feet per second, feet per second, feet per second, and feet per second. Is that what everybody got when you did the rate of change? It's all divided by 2. It's whatever this is right here. It's whatever this is divided by the 2 seconds, correct? All right, so I want you to check something. I want you to notice something here. What would happen if we did this? What do you notice? What is the rate of change for these guys? It's going down by how much between negative 32 and negative 96? So negative 64. All right, how about between negative 96 and negative 160? Ah, you seeing something here? And what about between negative 160 and negative 224? Down by another 64. What do you notice about this? This is what we call the second difference. Difference. This is the second difference, isn't it? We did the first difference, and now we're doing the second difference. The second difference tells us, if the first difference tells us it's linear, what do you suppose the second difference tells us it is? To the second power, which is quadratic. If I wanted to know it was cubic, what do you suppose would have to be constant? The third difference. So we can tell if a function, what degree a function is to by looking at its progressive differences over the same interval. Does that make sense? So if the first difference is the same, constant, then it is a first degree, which is linear. If the second difference is constant, then it is a second degree, which is quadratic. If the third degree is difference is constant, then it is a third degree polynomial, which is cubic, and so on and so forth, okay? So second difference tells us, since the second difference is constant, which is quadratic. So that's a way we could test to see if something's quadratic. Look at the second difference. If the second differences are all constant, then it's quadratic. Just like we look to see a test to see if it's linear is if the first differences are all constant. So, number 6, was the penny speeding up or slowing down or staying the same? Speeding up. How do you know it's speeding up? Yeah. Use what you know. The average rate of change increases in a negative direction. The negative direction only tells us which direction it's falling, doesn't it? My hand gets ahead of my brain. For each interval. Okay. In other words, it's a faster rate each time. So now it says graph y equals h of t. So we started at 1250. Then we went to where? 1186? So 1186 would be, oh, I don't know. At 2 seconds, 1186 would be about here. And then 2 more seconds is at 994. 2 more seconds is at 674. And 2 more seconds is at 226. And then we know somewhere just before 9 it hits the ground, doesn't it? So we can see this is, oh God, y'all don't know how hard it is to draw on these tablets. So we could see that it's doing this, isn't it? Sorry. Okay? So, is the graph concave up or concave down? Concave down. So what does that mean in the context of the problem? It means what? Yeah. Here we go. Let's tie this into what we've just been looking at here, which is rate of change too. What do we notice here? What is the slope right here? 0, isn't it? But then what happens to the slope here? And then the slope here. And then the slope here. What do you notice about that slope? It's getting what every time? The slope is getting steeper in a negative direction every time, isn't it? In other words, the slope is decreasing rapidly. Okay? So it's falling faster and faster, isn't it? I know the bird is hypnotizing, isn't it? Let's wrap this one up and let's figure out what we are supposed to take from this. What did we learn in this one? I hope you guys like this. I know it's very different than how you're used to learning, and I do apologize for that. I know you're used to just sitting and listening to me do notes or the teacher give notes. I hope this is actually better. At least you're doing something, right? You're actively kind of trying to figure out what's going on, aren't you? That's not a bad thing. That's actually going to make you a much better math student in the end. Because now you can figure it out rather than having to depend on the teacher to tell you what's going on. And as far as I can tell, most of you are doing a really good job of this. You're picking stuff up. Now we're just going to wrap it all up together. That's really my job in here, is to help you wrap it all up. Learning target 1. What did we learn? Quadratic functions have a constant fill in that blank. A constant what difference? Second difference. They have a constant second difference, don't they? All right. Now, what does that mean? It means the rate of change over each interval, and this would be the first difference, right, is going to grow or decline linearly. Now, learning target number 2. Average ROC means what? Rate of change. That is what? The change in the output divided by change in the what? Yeah. Do you know why I don't like to put change in y over change in x? In this, did we use y and x? So maybe it's better to think of it as change in output over change in input, because maybe it's t and h this time, or maybe it's something else. In this class, in pre-cal, what you're going to get is a lot more of these types of problems where we're looking at stuff that's not an x and a y. And I want you to be able to make that transition in your head very easily. Okay, what's the input, what's the output, right? Input is our independent variable, output is our dependent variable. So change in output over change in input. All right? And then per what? Per unit. In other words, in our case, per unit was what? Feet per second. Something per something, right? So for example, feet per second. Now, for this to be second difference, what do we know? What does second difference being constant really mean? The rate of change of the rate of change, doesn't it? Think about it. Second difference is we're really just doing the rate of change of the rate of change. So, now, last one is where we talked about concavity, isn't it? How do we know if something is concave up, or how do we know if something is concave down? So if something is concave down, that would look like this, wouldn't it? So what do we know about the rate of change? The rate of change is doing, and y'all don't have to draw this, but I want to show you. It's steep, it's less steep, it's even less steep, it's 0, then it goes and increases again, doesn't it? So the rate of change for something to be concave down, if we look at the rate of change, the average rate of change is going to be decreasing, and then it will be what? Increasing, won't it? So the average rate of change is decreasing, okay? So the average rate of change is decreasing. Now, what if it is concave up? What's happening there? And if you haven't noticed yet, what we're really looking at is that second half, aren't we? Here it's doing what? And here it is decreasing, isn't it? In other words, it's becoming more positive, isn't it? Increasing really in this case means more positive, and decreasing in this one really means more what? negative. Okay? So now you check your understanding. You guys are going to do that for homework, right? Everybody realizes that. There's 2 questions here that you have to do that have to do with rate of change. Is the graph up or down? Support your answer. How does this support your answer in part B? You guys link this to what our learning targets were, okay? All right, so now, rest of this class period, we are going to be building on what we're going to be studying next. It says build a library. Do we know what all of these functions look like? You may go back to your original place, okay? Somebody left the calculator. All right, so building a library. What does it say? Today we're going to look at 6 parent functions and explore their basic properties. Draw each of the graphs without the aid of your calculator. So f of x. Give me some x values we can plug in here. F of x equals x. So what x values would you like to plug in here? Give me a negative x value. It's got to fit on this graph, so negative what? Negative 3. If I plug a negative 3 into that function, what do I get out? Negative 3, don't I? Think about it. F of negative 3, I just plug in negative 3, don't I? So if I plug in negative 3, I get out negative 3, don't I? Isn't that how it's going to work for everything? What if I plugged in 1? What would I get out? 1. If I plugged in 5, what would I get out? If I plugged in 10, what would come out? Input is 10, output is 10. Do you notice they're both the same? Do you know what this guy is called? The identity function. Does that make sense? Why it's called the identity function? The input identifies the output, doesn't it? Because they are exactly the same. Y equals X. So let's plot this. Negative 3, negative 3. We said 1, 1. 5, 5, and 10, 10. So what are we going to get here? We're going to get a line that looks exactly like this, a straight line that goes through the origin, doesn't it? So this is y equals x, or f of x equals x. So I want you to look at this equation and look at this graph. There are rulers in the buckets at the end of in the wells there if you need a ruler to help you with any of these, okay? So tell me, what is the domain of that function? Yeah, all real numbers. You can plug anything in, can't you? Well, if you can plug anything in and it's the identity function, what can you get out? What are the outputs going to be? All real numbers. Good. What is the x-intercept? In other words, where does this cross the x-axis? 0. What is the y-intercept? Where does it cross the y-axis? That's 0. Where is this thing increasing? Reading it from left to right, where is it increasing? Everywhere? From left to right, isn't this thing just going up everywhere? So how do we write that as a domain? From where to where? From negative infinity to positive infinity. So it increases on the interval from negative infinity to infinity. So if it's always increasing, where is it decreasing? Nowhere. It doesn't. All right. So now, what is the function f of x equals what? What do those 2 lines mean? Absolute value of x. So let's plug some points in. Let's plug in some negatives. Let's plug in some positives, right? How about -1, 0, 1, and 2? If I plug in -1 there, what am I going to get back out? +1. If I plug in 0, I get 1, I get, and 2, I get 2. It almost looks like the identity function, except that on the negative side, this negative side down here, does everybody get it? This guy's almost just like this guy is, except for this. All of these values, the y values, are no longer going to be negative. Where are they going to be? They're going to be positive, aren't they? So this side is going to look the same. And this side, instead of being down here, if you make them all positive, they're going to look like this, aren't they? So this is why it looks like a V. It's like the negative half of the identity function went and became positive. Make sense? All right, so let's graph that guy. We've got -1, 1, 1, 1, 0, 0, and 2, 2. So it's going to go like this, and it will go like that, won't it? All right. So now, what's the domain? Yeah, all real numbers. However, what is the range? They're what? Greater than or equal to 0. So we're going to say for the range that the function f of x is greater than or equal to 0. We know f of x means y, don't we? So y is greater than or equal to 0. Get used to writing f of x instead of y in this class, okay? So what is the x-intercept? What's the y-intercept? Where is it increasing? Yeah, it's increasing from 0 to infinity. Where is it decreasing? Yeah, from -infinity to 0. Remember, we always read it from left to right. So this is absolute value. All right, what's the next one? What type of function is it? F of x equals x squared? Quadratic. Again, let's start with -1, 0, 1, and 2. If I square -1, what do I get? 0 is 1, 1 is 1, 2 is 4, isn't it? So -1, 1, 0, 0, 1, 1, but now we go to 2, 4. We know what this looks like, don't we? And then 3, 9. Actually, I think it's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9. Okay? So it's going to look like a parabola, isn't it? All right, so what's the domain of a quadratic function? What's the range? Greater than or equal to 0. Good. X-intercept, y-intercept? Increasing on? Decreasing? -infinity to 0. Boy, those are the exact same stats you have on an absolute value function. The only difference is absolute value is linear on both sides, right? And quadratic is curved, correct? All right. Now, f of x equals x cubed. What type of function is this? Cubic. It is a cubic function. Let's plug in some values. -2, -1, 0, 1. Cube -2, what do we get? No, we don't. -2 times -2 is positive 4 times -2 is -8. Cube -1, what do you get? negative 1. Cube 0, and cube 1, you get 1. So we have 0, 0, 1, 1, negative 1, negative 1, and negative 2, negative 8. So if we do positive 2, we'd also get positive 8, wouldn't we? So this thing looks a bit like this, does it not? So take a second and see if you can fill in the domain, the range, the x, the y-intercept, and the increasing and decreasing intervals. What do you think? I think you can do it. No. Man, that sucks. Sorry, my husband's at home. He had surgery on Monday, like you guys know, and he's at home by himself for the first day today. He said he just texted me to tell me he had a really bad coughing fit, and he's afraid he might have popped a stitch or two. I was like, that's a bad coughing fit. So, all right, so the domain was, range was also, x and y-intercepts are still 0, 0. This thing is increasing everywhere, isn't it? And then decreasing nowhere, never, right? All right. What type of function is this guy? Square root, yes. Now, here's my question. What kind of values can I pick for x for this guy? Well, numbers that you take a perfect square of, but what kind of numbers can I not pick for this guy? What? Negatives. I cannot put negatives underneath that radical, can I? So I need to start my x's at 0, maybe 1. What's the next good number after 1 to pick? 4, and then 9. Square root is 0, 1, 2, and 3, correct? Let's graph this guy. 0, 0, 1, 1, 4, 2, and 9, 3. So this guy is going to look like this. So there is a domain and a range restriction here, isn't it? This is not the same type of function. So what is the domain for this guy? X is what? Greater than or equal to what? 0? How would you write range? F of x is what? Yeah. Greater than or equal to x-intercept, y-intercept? 0 and 0, right? Increasing from where to where? Good. 0 to infinity. Decreasing where? Nowhere, right? It is not decreasing ever. All right. Last but not least, we have, what type of function is this? Yes, reciprocal. Heard somebody say it. It is a reciprocal function. So let's pick some numbers. Let's pick -2. If I plug in -2, what do I get out? Yeah, -1/2. If I plug in -1, what do I get? -1. If I plug in 0, what do I get? 1 divided by 0 is what? undefined. It is undefined there. It means there is a vertical asymptote there, doesn't it? So there is no value at 0. Plug in 1, I get, and 2, I get positive 1/2. So -2, -1/2. -1, -1. Nothing here. So I know what's going to happen here is it's going to go like this, getting closer and closer and closer to the y-axis. Do you know what it's going to do on the other side? It's also going to do this, getting closer and closer and closer to the x-axis. Anybody tell me why it's going to get closer and closer and closer to the x-axis? Yeah. What happens as this value gets bigger and bigger and bigger? 1 over 10, -10, 1 over -100, 1 over -1,000. It gets smaller, doesn't it? Which means it's, like you said, getting closer and closer to 0, isn't it? So what is the other side going to look like over here? This, except it, yeah, it's going to be here, isn't it? It's going to get closer to 0 here at the y-axis, and it's going to get closer to the x-axis, isn't it? Okay. But it's never going to actually touch the x-axis or the y-axis, is it? So let's start with that. Does this thing have an x-intercept? None. Does it have a y-intercept? None. All right. So let's talk about the domain. What are the domain values? The way I need you to think about this is it can be anything except what? 0. So we can write it that way. We can write x such that x does not equal 0, where x is an element of the real numbers. Guys, this is what we call set builder notation. Huh? Oh, x is an element of the real numbers. That little e means element of. It tells you which set of numbers it is. It can be anything except, what we're basically saying there is x can be anything except 0. So guess what we can do for y? Y can also be anything except what? 0. So we're going to do, instead of x, we're going to do f of x such that f of x cannot be 0, where what? F of x is an element of the reals. Now instead of f of x, we could just put y's and all that, couldn't we? But we're getting used to writing f of x, so we're going to do it that way. Now, where is this thing increasing? This is tough. Read it from left to right. So from left to right, it's going down, and then it's still going down. So is it increasing anywhere? Never. Where is it decreasing? Everywhere except what? At 0. We can't write this as that way, so we have to do the intervals. So it is decreasing from -infinity to 0, and then from 0 to infinity. Seems weird that we can't write as all real numbers, doesn't it? Decreases everywhere. It doesn't. Because at 0, it's not doing anything, is it? Because 0 is undefined. Do you have a question? U means union of. That's what we stick in between when we do intervals and stuff like that, where we have more than one interval. We put U's between them so that we know that it includes all of those things. So we got a few more minutes before lunch, so let's figure out Basically, by writing it this way, we're indicating that something's happening at 0. Does that make sense to everyone? All right, learning targets, and then I'll let you guys will have time to do your check understandings in class. So that'll be nice for, maybe you won't have any homework this weekend? Wouldn't that be lovely? Learning target number 1. What is a parent function? A parent function is defined as the simplest function of a family of functions. So what are families of functions? They are functions that share a common characteristic, right? We say that by saying they share similar algebraic properties, graphs, and behaviors. Okay? What are some of the examples we saw as families of functions? Yeah, those 6 we just did. Linear, which were identity functions, quadratic functions, cubic functions, square root functions, inverse functions, all of those 6 that we just saw. Okay? All of those, hey lady, all of those are families of functions. Oh, you get it done? Yeah, sure.
Thank you. Sorry, I didn't know you were...
No, it's fine, we're finishing it. Oh, difference here, you just need me to fill out my name.
Yeah.
It's basically like the line. So this is left to right, this is up and down. This is
Hang on. You gotta wait for the next bell. You have much third block. Oh, is it not third block?
this is
It's second block. Oh, duh. All right. There you go. See? You're welcome.
Okay.
Not bug. This whole lunch thing is freaking me out.
I know, it's so confusing. I hate
Yeah.
this.
Me too.